I read my manuscript. So, uh, hello everyone, I'm Jong Nam at the University of Rochester. I've been studying the mechanics of the hair bundle and the organ of Corti. I appreciate the mechanics of hearing organizers, Bastian Ebb and Wei Dong, for leading this effort. I will assume that the audience may welcome some refresher regarding hair cell anatomy, and they are interested in physics and mechanics aspect of hair bundle mechanotransduction. The two-thirds of this talk is regarding current knowledge of hair bundle mechanics, while the latter is, is some examples of myself, from my lab. This is later disturbing. I will close. Okay. So the left microscope images is scanning electron microscopy of hair bundles from the turtle utricle. Two hair bundles for each figure are shown. Although SEM images are informative, sometimes these images provide misleading impression, as if the hair bundles are very compliant. Actually, they are not this compliant. There are some mechanical similarity between hair bundles and the tall skyscraper buildings, like this one, 828 meters tall Burj Khalifa in Dubai. Both structures, hair bundles and tall building, are founded on fiber reinforced base. Both structures are tapered. Notably, both structures are subjected to similar angular displacement. This Burj Khalifa, by normal operating condition, deflect by 2 meters at the tip. That is comparable to 24 nanometers vibrations of a 10 micrometer tall hair bundle. So in angular displacement aspect, they are comparable. The other shared characteristic is that both structures are active. Both structures adapt themselves to external mechanical stimulation. Hair bundle consists of stereocilia bound by numerous interciliary filament. The panel A shows top-down view of a hair bundle. There are the numerous filament between the circles, which is stereocilium. They are connected by numerous fibers. In the side view, like panel B, the hair bundle stereocilia are arranged like a staircase with a monotonic height gradient. At the tallest end of hair bundle, there exists usually one or no kinocilium in a bundle. K here indicate kinocilium. In auditory hair cell bundle, the kinocilium disappears as the stereocilia develops. Among different interciliary filament, thin stand out. Unlike other interciliary links that run all three hexagonal axes, thin run in one direction along the steepest height gradient. Unlike other interciliary links, thin run obliquely from tip of stereocilia to the shaft of its neighboring taller stereocilia. Hair bundles come in different shapes. They have very different shapes depending on organs. In panels A, B, and C are from red cochlea. A and B are out hair cell bundles from two different frequency locations. Panel C is the hair bundle from the inner hair cell of red cochlea. Inner cell hair bundles look like the sail of a boat, as you see. It's good for fluid stimulation. Panels D through G are utricular hair bundles. Panels D and E are from mouse utricle, and panel F and G are from turtle utricle. This thin and long hair bundle in H is from turtle semicircular canal. This is very tall. In general, the hair bundles from high frequency organs, they have a smaller number of rows and more columns. Like this outer cells, 3 rows and like 15 to 20 something columns. In extreme case, like the back cochlea, which here is like 60 kilowatts, 100 kilowatts. Some hair bundles only have 2 rows in that cochlea. If you see panel F, this one has more rows than columns, which is in low frequency organ. So that's something we find from the bundle shape. Although the stereocilia bundle comes in various shapes, there are shared characteristics also. So that the stereocilia are bound by fine filament. It has monotonic height gradient, right? And they are connected by Tim links that runs along the steepest height gradient. Those characteristics are shared among different hair cell bundles. The minimum unit of a hair bundle is the stereocilium, and this is the microstructure of a stereocilium. Stereocilium consists of a cylindrical shaft and a tapering rootlet. The shaft of the stereocilia are packed with a few hundred actin fibers. These lines, strips, are actin fibers, and they are also bound by filament actin fibers, indicated by these arrowhead. And a few dozen actin fibers rooted deeply into the rootlet and inserted into the apical surface of the hair cell called the cuticular plate. And often this rootlet is dense in electron and look darker in this electron microscopic image. The minimal unit of hair bundle is consists of 2 stereocilia connected by fibers. So here, let us consider the compliance of the stereocilium. This equation is one form of beam equation. So angular displacement over length is proportional to the moment applied to the beam and inversely proportional to the flexural rigidity EI, where E is the Young's modulus of the material and I is the second area moment of inertia of the cross section, either AA or BB here. Area moment of inertia is proportional to the radius to the power of 4. That means if the rootlet is a quarter thick as compared to the shaft, the flexural rigidity of the rootlet is 256 times more compliant. The rootlet is 100 times compliant than the shaft. And in this derivation, I discussed as if this material of stereocilium is isotropic, which is not the case. If you see the ultrastructure of the stereocilium, in the shaft AA, the actin filament are cross-linked by numerous filament among them. It's like green-colored linkers are connecting them between actin fibers. They prevent shear deformation between actin fibers. In contrast, if you go to rootlet like the panel, the cross-section BB, there are much less cross-linking between actin fibers. Instead, entire rootlet bundle is bound circumferentially by some binding protein. So kappa R here indicate the rotational stiffness of the actin bundle. It can be represented by this equation. Again, the E times section modulus. This time I0 means that the secondary moment of inertia of a single actin fiber, and the small n indicate the number of actin fibers in the bundle. And H is the rootlet height, and multiplied by alpha. Here, alpha is important one. Depending on cross-linking, alpha can be 1 when there is no cross-linking. When it's fully cross-linked, very tight cross-linking, the alpha will be R divided by R0 squared. R is the radius of entire rootlet, and R0 is the radius of a single actin fiber. So this ratio can again be greater than 100. So this means that even the same form factor, macro, the dimension, the shaft and the radius, same dimension, depending on the cross-linking extent, the compliance changes a lot, depending on allowing shearing or not, right? So combining these two, rootlet, because of its thinner than the shaft, second, it has less cross-linked than the shaft, rootlet should be much compliant than the shaft. And experimentally measured the rotational stiffness of rootlet, interestingly, falls between these two extremes, no cross-linking and full cross-linking. Then let us consider kinematics of hair bundle. More specifically, why thinlings are running obliquely, unlike other interciliary filament. Thinlings are interesting and important for hair bundle mechanics because the lower end of the thinning is connected to the mechanotransduction channel, and the upper end of the thinning is linked to the actin core through the myosin motors. Therefore, thinning could deliver some force generated from either mechanotransduction channel or myosin molecules to hair bundles. Let us consider a simplified model of a hair bundle. I just convinced you that the rootlet is very compliant. So the two stereocilia are represented by this rigid bar pinned at rootlet and connected by two elastic links, one representing thinning, the other one horizontal connectors. And the hair bundle deflected by distance x, while the horizontal connectors A doesn't change its length. However, depending on the direction of bending, the obliquely running thinning length changes. Here, delta represents the length change of the thinning, and x is the linear displacement of bundle tip, and is approximated by the geometric factor gamma here, which is represented by the stereocilia separation divided by bundle height. So in short, summarized, the hair bundle is designed in such a way that the overall bundle deflection is delivered faithfully to the molecules of our interest. We can transduction channel very efficiently without deflecting unnecessary structures. This is the statics aspect. The hair bundle can minimally represented by two elastic components. One is the torsional spring at the rootlet, and the other one is the gating spring or thinning complex spring running obliquely along thinlings. If we turn this rotational model into linear model, this is bundle tip displacement. this because of this transformation from angular motion to linear motion, we need this factor, this gain factor, and this the height squared. Overall, hair bundle stiffness is proportional to the number of stereocilia n here, and inversely proportional to the height squared. There are many measurements of hair bundle stiffness because hair bundle stiffness is very fundamental property that can contribute various aspects of hearing or balancing function of inner ear organs. And there are three popular methods to measure hair bundle stiffness. One is using calibrated microfiber. In that method, they first measure the compliance of this microfiber, and then the microfiber tip is attached to hair bundle tip, while the base of microfiber is driven by an actuator. So known distance is moving in the base, and the hair bundle is deflected. This microfiber method can be represented with this model mechanical diagram here. So this KHB is hair bundle stiffness, and KP is probe stiffness, and then X1 is the probe tip displacement. We drive the probe base, not tip, probe base, and the X2 is the deflection at the hair bundle tip. X2 in this diagram is measured by a pair of photodiode by differential current between this photodiode. They measured the bundle tip displacement X2, and the hair bundle displacement can be represented by this equation using probe stiffness and the deflection of the hair bundle. Using this method, the Crawford and Ferriplace try to test that the relationship of hair bundle stiffness, that hair bundle is hinged at the rootlet by showing that compliance, whether the compliance is proportional to the height squared or not. So they changed the force application height and measured the stiffness. And if hair bundle is hinged on rootlet, it will follow the parabolic relationship, the force application height versus compliance. And this solid curve indicate the parabolic relationship. Other method that have been used to measure hair bundle stiffness is using fluid jet. This method also need a stage to estimate the force. The way they do is that they make a glass probe, cantilever probe that have a similar dimension as hair bundle. The typical hair bundle dimension is a few micrometers. They may place the probe the same distance and angle as hair bundle there, and they apply fluid jet. Fluid jet is driven by some voltage of driver, and they measure the deflection of their structure. From there, they could relate the driving voltage of fluid jet with the fluid force that is subjected to the structure. And then they replace the probe location with the hair bundle and measure hair bundle displacement versus driving voltage of fluid jet. From that relationship, they obtain the compliance of hair bundle. When they calibrated carefully, their stiffness values were comparable to probe method. The third method I would like to introduce is using thermodynamics principle. Hair bundles are microstructure immersed in water. So without any external stimulation, hair bundles fluctuate due to Brownian motion, right? For 1 millinewton per meter stiffness hair bundle, the fluctuation is as large as 1 or 2 nanometers. So what is the earliest experiment performed by Dink, Webb, and Hotchkiss? They just measured the fluctuation, noise of a hair bundle tip. And this is the power spectrum. Y-axis is power spectral density, x-axis is frequency. And they curve it with the obtained data with this equation. In this equation, this KB is Boltzmann constant, T is absolute temperature, the small k is the stiffness of the structure, and the C is damping of the structure. So this method not only gives the stiffness, but also can estimate the viscous drag applied to the structure. Using this method, Bashtonov et al. Tried to estimate the interciliary link stiffness. They did the same measurement as Dink, Webb, and Hotchkiss. So this thick line is the power spectral density of intact cochlea. Then they applied some chemicals to disrupt specific interciliary links. In this case, they used the beta calcium buffer to disrupt the thin links. As expected from mechanics, this high frequency region dominated by this viscous drag is hardly affected by disruption of thin links. However, in low frequency region, which is dominated by this elastic property, affected by disruption of thin links. So the vibration amplitude increased, stochastic the fluctuation increased. These two ratio here in this subset indicate the compliance increase due to disruption of the thin link. So like a factor of 2 is twice as compliant after disruption of the thin link. The third one is my computational model studies imitating, reproducing Bashtonov et al. Result to using 3-dimensional model to obtain the interciliary link stiffness, and the thin link property adjusted until it becomes comparable to Bashtonov et al.'s result. This table summarizes the stiffness measurement. This is subset, not exhaustive. What I included is some earlier studies and those recent studies that are more dedicated to stiffness measurement. I apologize for small font size, but if I read this table for you, glass fiber method has been most popular method, followed by fluid jet, and Brownian motion measurement are relatively rare. The popular animals are bullfrog secule, mouse, chick, and rat cochlea or vestibular hair cells, and turtle also cochlea hair cells. Stiffness values, that is our most interesting part, ranges 3 orders of magnitude from 10 micronewton per meter to 10 millinewton per meter. One thing notable is that not all stiffness are equal. Some stiffness measurement are steady state stiffness. Some stiffness were measured instantaneously. Depending on timing, the stiffness value changes a lot. This matters when hair bundle, if hair bundle is active. If hair bundle is passive, stiffness is stiffness, right? So there is no transient stiffness. However, hair bundle is not passive. That's what I'm going to tell in the following slide. I will now introduce the channel kinetics and how mechanotransduction channel interact with the passive hair bundle. This is the pioneering effort to measure hair bundle mechanotransduction. Corey and Hotchkiss in 1977. They isolated the bullfrog seculus, the macular surface, and applied glass probe to hair bundle to deflect hair bundle, and at the same time they measured intracellular potential. In here, this sawtooth pattern is the mechanical input to the hair bundle, and these top three curves are the intracellular potential measured at different stimulation level. When the stimulation is smaller, the response pattern follow the stimulation sawtooth pattern well. However, as the stimulation level becomes greater than 1 micrometer, the receptor potential pattern didn't follow the sawtooth pattern because mechanotransduction saturated. Panel B is the relationship of receptor potential versus bundle displacement. It shows the operating range. Hair bundle mechanotransduction is sensitive within certain displacement range. It's called the operating range. In this specific case, this measured hair bundle is sensitive between negative 0.3 micrometers to 1.2 micron, positive 1.2 micrometers, right? And as the measurement method refined, recent studies showing narrower operating range than earlier studies. As I know, this is the earliest measurement within the mammalian auditory organ. Russell and Selig in 1978 used guinea pig cochlea, and they measured the mechanotransduction signals from the inner hair cell. And they made several exciting observations. When they applied tone tips, they found that there is DC offset of the receptor potential. Not only AC, but they also DC offset during stimulation. Other interesting thing is that they observed the nonlinearity in the receptor potential versus sound pressure level applied to the inner ear. And they also found that the receptor potential is sharply tuned at certain frequency. These observations were reconfirmed in follow-up studies. Hair bundle has the polarity. Shadell, Jacobs, and Hotchkiss showed that if 0 degrees is the most sensitive direction of stimulation along the steepest height gradient, when they stimulated the 90 degree from the EI axis, excitatory inhibitory axis, the response was minimal. The bundle was minimally sensitive. So the hair bundle has preferred direction for stimulation. This polarity is relatively less important in auditory organ because all hair cell bundles are running in the same radial direction. However, when it comes to vestibular organ, this polarity can matter for its function. Shown in the right is the macular surface of the turtle utricle, and this arrow indicates excitatory direction map of the hair bundles within this surface. This thick black line is called the polarity reversal line. Along this line, polarity reverses. Like this vestibular organ, hair bundle polarity matters for its function. Adaptation is also a very intriguing characteristic of hair cell bundle mechanotransduction. This measurement done in fat place lab, the hair bundle is subjected to different level of displacement, and the displacement was sustained for a period. While displacement is sustained for a period, the current peaked and quickly decayed to almost 0 level. This decaying of current over time under sustained stimulation is called adaptation. In this case, measured in rat cochlea, like the characteristic frequency 4 to 5 kilohertz, this adaptation complete within 1 millisecond, for example, in this case. In this experiment, they first applied a step displacement 0.4 micrometers. On top of the 0.4 micrometers, they applied another family of step stimulation and measured the current. Despite 0.4 initial displacement, overall current patterns are quite comparable to the response when there was no initial DC offset. This curve in panel C shows the current versus displacement relationship. These empty circles are from panel A, while these filled circles are from panel B, these responses. So this current versus displacement relationship parallel shift by nearly 0.4 micrometers. So this means that hair bundle mechanotransduction reset itself. If it's maintained to a certain level for some limited time, then it resets its sensitivity and it just behave as if it's fresh hair bundle. This adaptation, like shift over IX relationship, could be achieved by changing intracellular calcium level. If changing the calcium level, this IX relationship can shift. The adaptation can contribute to function, for example, in the gravity sensor. Say that assuming a scenario, we tilt our head to the left, and this red arrow indicates the direction of gravity. Then due to the mass of autocorneal layer, the utricle will shear. The layer between stiff autocorneal layer and the stiff epithelial layer, there is elastic gel layer where hair bundles reside. It is subjected to shear because of this gravity. If you think about along the macular surface of this broken line, this is a cartoon along the imaginary broken line. There are 4 hair cell bundles are activated, while 1 hair bundles in opposing direction will be inhibited. So for some time, due to adaptation, these 5 hair cells will reset and become fresh and be ready for next head motion. Right? So adaptation can achieve high sensitivity while having wide operating range. So adaptation can help for that purpose. However, this explanation works for DC sensor, like gravity sensor. Would that work for the AC sensor, where there is no DC offset by head tilt like that, like cochlea? So we need a different theory. Here is one theory. For example, Rich and Ferriplace claimed that the adaptation can help for selecting frequency. Adaptation, if the stimulation applied very slow, due to adaptation, the signal will be decreased. If the stimulation is applied much slower than adaptation speed, there will be no signal detected. So adaptation behaves like low pass filter. No, the opposite, high pass filter, sorry. On the other hand, the channel activation and the deactivation, it takes time. So if the stimulation is much transient, then the channel activation deactivation time is too fast. The stimulation cannot be detected. So the channel activation and deactivation can behave like a low pass filter. So combining channel on and off kinetics and adaptation, it can form a band pass filter, right? That can help narrowing down the frequency. However, the one limitation of this theory is that the physiological tuning is much sharper than these first order filters can provide. So this bandpass filter by adaptation may not be the primary filter. It may be just assisting the primary filter. There is more progressive theory regarding the adaptation. It was observed that some hair bundles can oscillate spontaneously. It was observed that bullfrog-secular hair bundle in right condition, they can spontaneously oscillate by themselves. And Martin et al. In 2003 and Wilfan and Duke in 2003, they came up with a theory including channel activation and adaptation. They explained this spontaneous oscillation with the theory that the fast stroke of the oscillation is explained by channel opening and closing, and the slow stroke is explained by adaptation. So the adaptation and the channel opening and closing explains spontaneous oscillation. And in this scenario, adaptation motor's role is to place the hair bundle in the vicinity of hope bifurcation, in the vicinity of instability. If hair bundles are unstable, for example, this spontaneous oscillation frequency exists. If the stimulation, external stimulation comes at the matching frequency as the spontaneous oscillation, it will boost the external stimulation and it vibrate more. However, if the opportune stimulation comes with the spontaneous oscillating hair bundle, they interfere each other. Stimulation and the hair bundle's own oscillation will interfere each other and will suppress the spontaneous oscillation. Therefore, this adaptation mechanism, could help to select certain frequency. But actually, this Martin et al. And Wilfan and Duke argued in their paper in 2003 is more than this the frequency selectivity. They argued that this mechanism is the amplifier of this organ by doing this one. However, presently, this amplification by hair bundle is not the prevailing theory regarding at least mammalian cochlear amplification. So combining the active, the channel kinetics with the hair bundle, Howard and Hotchkiss in 1988, they presented a concise theory that are supported nicely by their data. In panel A, they applied step force, and the top plot is the bundle displacement due to step force applied, and the second graph is the mechanotransduction response, the receptor potential response, and the bottom one is the representing the step force by the displacement of a probe base movement. As you see, the bundle tip motion and the transduction response are not monotonic. They repeated this experiment at different stimulation level and obtained the bundle stiffness versus displacement relationship. What was interesting was this bundle stiffness was not constant. Considering this displacement of 100 nanometer is infinitesimal compared to the bundle height of approximately 10 micrometers. For passive structure, we expect there be no nonlinearity and the bundle stiffness may be flat. However, there was reduced stiffness in some displacement region. And interestingly, that most compliant region coincided with when the transduction channel is most sensitive. when they abolished the transduction, the bundle mechanics became linear again. So this bundle's nonlinearity, mechanical nonlinearity, related with the channel's activity. So this is the first concise explanation how channel kinetics combine with the bundle mechanics and affect the bundle mechanics. To explain what's happening in here, minimal of 3 equations are needed. First one is the bundle mechanics. Here C is the viscous drag applied to a bundle, and Kg is the bundle, Ks is the bundle stiffness when it's summed up with the gating spring stiffness. These two terms are from mechanical transduction channel. XA indicate the bundle motion due to adaptation motor, and the P naught is channel activity, mechanical transduction channel open probability, whether it closed or open. So the channel action affect bundle mechanics is the essence of this equation. The second equation defines PO, open probability here, and the channel open probability is a function of bundle mechanics. And the adaptation X sub A is defined by this equation. This is the, among many different theories, this is the simplest version. Ka is the adaptation speed, and XA0 is the set point of resting tension maintained by adaptation motor. So I prepared a cartoon version to explain the theory graphically. Here are some symbols for the graphical explanation. This green bean-like shape is mechanical transduction channel. In this one, it looks like the channel is closed, and the this is the tip link, and the color of the tip link indicate the tension in the tip link, and the slow and the fast adaptation motors are represented with the gears, and this color of the particles indicate either calcium or potassium ions. So with this the graphical model, I will follow this the mechanical transduction hair bundle mechanics response, how this model can explain this observed response. Again, this bundle is subjected to a step force, and the step force withdrawn, and by this step force, the transduction current changes over time, and the displacement, bundle tip displacement, this change over time. And as you see, they are not monotonic, and the mechanical transduction current displacement pattern are different. However, there exists intriguing correlation between current and displacement, and I will show you one representing theory that can explain this response. So at rest, the slow adaptation motor tries to maintain tension in the tip link at the about to open level, right? In this moment of time, this channel is closed, right? And then this red cross mark indicate in the graph or along time axis the state of this hair bundle and the transduction channel, no current and no displacement. As the hair bundle is pulled toward the polar edge, is the black line indicate the hair bundle tip displacement. Tension in the tip link increases, right? In this graph, the step force applied, channel is still closed, and the bundle deflected, right? As due to increased tension, eventually channel opens, and the tension in the tip link relaxed by the opening of the gate transduction channel, and this additional compliance indicated with the green arrow here, additional displacement due to channel opening, and due to electrical potential in and outside of the cell, cations, including potassium and calcium, flows into the cell through the mechanical transduction channel. As the calcium acts on some apparatus near the fast adaptation motor, it activates fast adaptation motor, and the channel recloses. As the channel recloses, it pulls the Tim link back, and the Tim link tension increase. As a result, bundle tip moves backward, right? So it's called in some experiment fast twitch. Bundle moves backward, like this way. And the mechanotransduction current decreases because of some channels reclosure, right? However, I have to tell that this is the part where the most various theories exist, and even experimental observations are different from experiment to experiment. So there are alternative theories, including these studies here. So this is one of the existing explanation. And finally, increased Tim link tension is adjusted by slowly moving adaptation motor. As the adaptation motor relaxes the tension in the Tim link, the bundle deflect further toward the positive direction in this red cross marks here. So thus far, it is the very simplistic hair bundle model, lump parametric model. And I switch gears here to introduce a couple of my own studies that showing that how the three-dimensional hair bundle mechanics could affect their function. I show two example studies. We studied to test the hypothesis that there exists experimental artifact of the popular experimental method, and because of that experimental artifact, some key mechanotransduction parameters could be either underestimated or overestimated. We try to test this hypothesis by popular experimental technique. I mean the probe technique. So hair bundle was modeled using finite element method. With the stereocilia were represented by beam element that can explain both axial bending and the shear deformation, and the interciliary links were represented by link element that can sustain only axial displacement. The model represent rodent outer cell hair bundle, more specifically let outer cell bundle from apical region 4 to 5 kilowatts. The other part of the model is channel kinetics. We assumed that channel has 4 subsections. Each one can bound to calcium, and each calcium bound state can take either closed configuration or open configuration. Although look complicated, this kinetics can be defined by 2 rate coefficients. One is calcium binding and unbinding coefficient that will determine the speed of fast adaptation, and the other rate is the channel opening and closing constant that determines the between closed and open configuration dynamics. In the FE model, the interaction between channel and the FE model is defined by this term F here. This F is the tension in the Tim link, and the tension in the Tim link at each time step computed from FE model, and that determines the channel open probability. Then if the channel open and close, the original length of the Tim link complex changes. The closed configuration, original length shorter, and the open configuration, original length is longer. For example, 170 nanometers, 171 nanometers changes original length. That changes FE model. Using this model, we simulated this condition of experiment. In this experiment done in Ferry-Place lab, they used the flexible glass fiber to feed into stimulate the outer cell bundle, V-shaped outer cell bundle more evenly. They dipped the tip of a probe into the elastomer, and they make the bulbous tip at the end of a glass fiber and feed into the V-shaped bundle, and the mechanical stimulation was delivered. Right? This was modeled with a computer model. This part is a bit um, less accurate. If we find a more accurate description, it looks like this one, bulbous tip, true dimension. So it's very large and fit into this V-shaped stereocilia bundle. If I give you some sense of this dimension, each stereocilium is 205 nanometers thick, and the operating range of this mechanotransduction of this hair bundle is considered less than 100 nanometers. It's the less than half thick of the stereocilia displacement is enough to saturate the bundle. It's that sensitive. So we made a contact model like this one. This red colored one is the bundle contacting with the probe tip, and the green one is about to attach or about to detach, and the gray one is not contacting surface. So with this model, first we simulated the ideal condition where the tip of hair bundle pulled uniformly. That is the desired condition, like a tectorial membrane. This left top graph shows the three-dimensional bundle deformation where the color indicates the displacement. And the left bottom one is top-down view. Each circle indicates individual stereocilium, and this red circle indicated the stereocilium with open channel, and the gray circle indicate stereocilia with the closed channel. And we applied a step force and hair bundle displacement and current response as the experimentalist obtained, and this is the response. As the step force is applied, bundle deflect and roughly maintained there. In the meanwhile, transduction current quickly decays due to adaptation. This step force applied for 0.6 millisecond, and that is enough time for this hair bundle's adaptation. And these channel responses are stochastic. So this is the ideal case scenario. And the second one is more realistic scenario. Probe tip pushes hair bundle, and these low columns of stereocilia will be pushed while this part will not be contacted. So what you see is that this part of transduction channel activate more, while non-contacting part will be less stimulated. It is not clear. Some is sticky and it pulled back right here, right? And it is not clear from here. So we simulated the different probe types and obtained the current versus displacement relationship. This thick black curve indicate ideal case. It's very sensitive, very steep. However, in this non-ideal case, this IX operating range expand a lot, as large as 1 order of magnitude or more, depending on probe types. Right. So this is what we argued, that experimental artifact. If you use this colored curve and assume the ideal stimulating condition, that result in misleading, inaccurate estimate of mechanotransduction parameters. I'll skip this part. That simulation was paralleled with the experiment by our colleagues in Stanford University, Tony Leach and Anthony Pang. Now Anthony is in Colorado, the University of Colorado. They used a similar experiment, different probe tips, and measured transduction response, obtained IX relationship, and as expected, better fit probe resulting in more sensitive, steeper IX relationship, unfit probe resulting in broad IX relationship. They also showed that the column by column separation in this cell-like inner cell hair bundle, they used fluid jet to locally, we can locally activate some separate columns of hair bundle, and indeed just separate columns activated by local stimulation. And if we use a wide mouth fluid jet and the entire bundle stimulated, right? So in terms of even a stimulation, fluid jet may be beneficial, right? The consequence of that, using this model, if we estimate the two important basic biophysical properties of mechanotransduction, gating spring stiffness and gating swing, and after correcting that, the gating spring stiffness is in the upper end of the compared to the other reported result, and gating swing is lower limit compared to other measurement result, and the single channel gating force, which is determines the sensitivity of mechanotransduction, is smaller end compared to the other literature. Of course, this is not necessarily because of experimental artifact. The animal species are different from this study and this study. Most are vestibular organs. This one is the mammalian auditory organs. Difference could come from the different subject. Second example is the utricular hair bundle responses. So what we focused is that these two hair bundles from the same organ look very different. We named it cell E and the cell S. Cell E has a very long protruding kinocilium plugged deeply into the steep autocorneal layer, while this kinocilium has the similar height as the tallest stereocilia, and it is probably connected to gel layer, which is considered soft, compared much softer than autocornea. Our hypothesis is that cell E is a static sensor measuring the position, the DC sensor position, while cell S is kind of motion sensor. It changes the movement of direction. In that scenario, having those two types of sensors subjected to different mechanical boundary conditions helps to achieve wide operating range while good sensitivity depending on stimulation type. So in this scenario here, this is entire utricle. This pink colored one is autocorneal layer, many stones there, and if head tilt, this one moves, and the head accelerate because of inertia. It also results in shear deformation between this pink layer and the green layer. It is represented by the single degree of freedom model, and then those two cells, cell E and the cell S, modeled using this three-dimensional finite element approach, and then the popular experiment applies step force, displacement, current, or simulated to obtain I-X relationship. I-X relationship surely because of the geometrical difference between these two cells are dramatically different. I have to tell that the mechanotransduction channel, because I have no evidence those two cells have different mechanotransduction channel, are exactly the same. This difference is purely from the bundle mechanics difference. So one cell I-X relationship is much steeper than the other one. Then we simulated a hypothetical scenario in the animal, the behavior. So this turtle, red-headed turtle, assume that in this light green part, it slowly tilts its head with 1 hertz. It's like 60 degrees. It tilts its head, and suddenly it stretches its head for feeding strike. So very slow motion followed by fast motion. So our scenario is that this slow motion is good for DC sensor, static sensor, while this red one, it needs a dynamic sensor. So these two cells, cell E and the cell S, may be dedicated to, one is for DC gravity sensor, the other one is motion sensor. So cell E is definitely is pulled by the autocorneal layer. So this is a fixed scenario. It follows the head motion during the head tilt, slow head tilt while cell S, if it is viscously clamped, it doesn't follow record this slow head motion at all, but fast motion it encodes quite well. fast motion cell E saturate in here in the top and bottom 0 to 1. If the cell S is displacement clamped, it saturates even slow head motion. So what they argue is that by using different mechanical stimulation type, elastical coupling, and viscous coupling, we can use different hair cell bundles for different sensing purpose. By doing so, we can achieve both wide operating range in static sense and the good sensitivity for that wide the operating range. To summarize what I have introduced in this slide in numbers, these numbers are relevant to rodent outer cells. Bundle height is on the order of a few micrometers. Stereocilium thickness, each stereocilium is on the order of a fraction of micrometers, 0.3 micrometers, for example. Number of stereocilia ranges from 50 to 100 typically, right? 60 is not a bad number. Stiffness of bundle is on the order of 5 millimeter per meter. For your reference, this is the stiffness of the basilar membrane in the apical region. Stiffness of Tim-link complex is comparable to the bundle stiffness itself, and the gating swing of mechanical transduction channel is on the 1 nanometer, and the resting tension in the Tim-link is on the tens of piconewton, and the operating range of hair bundle mechanical transduction is 30 nanometers, which in angular the range displacement is 0.5 degrees, and the faster adaptation time constant in the order of 0.1 millisecond, slow adaptation time constant a few milliseconds, and the mechanical transduction channel onset time constant may be less than even 10 microseconds. So remaining questions of this one is that we still do not know if hair bundle contribute to any kind of mechanical resonance in the cochlea. There have been theories about the tectorial membrane second resonator, but still we have not concluded that discussion. Does hair bundle adaptation contribute to hearing function? It is still open question how the hair bundle mechanical transduction adaptation affect hearing function. Are the cochlear hair bundles unstable? We do not know. For example, the cochlear hair bundle from the turtle are unstable, and the vestibular hair bundle from lower vertebrate unstable, but mammalian cochlear hair bundle unstable, we do not know. What are the shared principles of hearing across different animal classes? We do not know very well. But the unique principles for mammalian hearing is not very well defined. So these are widely open questions. Finally, I appreciate the support of my research and former and current collaborators. Thank you.